Hello, everybody. Welcome to today's session. So today, Graham Manuell is going to be doing the second last session on his workshop on point-free topology and constructive mathematics.
Thank you. Good. Thank you. Yeah, good. Okay, let's get started. So I want to start just by, I guess, so remember last week we did things on sublocales, and we spoke a little bit about preimages, but I just want to go through that a bit again. So the idea is, okay, so we have some sublocale of y, and we have some function f from x to y, and we can compute the preimage just by taking this pullback, just like you would in kind of any category. So it's easy to see that this pullback in set would just give you the preimage. And I'm saying this makes this sublocale lattice into a functor. So on objects, we're going to take for every sublocale, for every locale, we'll consider the lattice of sublocales. And then on morphisms, we're going to do this preimage operation. So this gives us a contravariant functor that takes us from locales to posets. And to see exactly what it does in algebraic terms, it's not so hard. So if this diagram's in locales, you have a kind of dual push-out diagram in frames. And if you work out what this actually does to the congruences, you see that if CS is the congruence associated to S, then the congruence associated to this pullback is given by just like applying F to the congruence, like the F star to the congruence component-wise, and then generating a congruence. And because we know that an open congruence is generated by just a single generator setting A equal to 1, when you apply kind of F to this congruence, it's just going to be the thing setting F of A equal to 1. So you can see that an open congruence will get mapped to an open congruence, and a closed congruence will get mapped to a closed congruence. So again, this is what we expect. We expect these continuous maps, right? That the preimage of an open sublocale is open and the preimage of a closed sublocale is closed. Okay, any questions about that? Okay, but there's another way to kind of do things. Rather than taking preimages, we can take images. So if we have a frame homomorphism, we can just do a normal image factorization, right? Where you just factor it through its image. And this is a regular epi monofactorization in the category of frames. So in the category of locales, this would be an epi regular monofactorization. And a regular mono in locales is just a sublocale inclusion. So this is a way to kind of factorize any locale map, and we can use this to define images. So if we have a sublocale of X, and then we apply a locale morphism F, we can just factorize that. And then the thing we get in the middle is going to be the image of F. And I'm calling this SF lower shriek. So the previous one, the preimage, I called SF upper shriek, upper star. And the reason for this notation is that it turns out this is left adjoint. So well, I've told you also exactly how you can work out in terms of congruences, what you do. Now you take the preimage under this map F star cross F star. And yeah, so it turns out for every F, the map we get in this, with this image construction is adjoint to the map we get with the preimage construction. And again, this is maybe what you would expect to be the case if you kind of know what happens with images and preimages in set. Okay. So yeah.
You said epi was regular, or the mono was
Yeah. So in the category of frames,
right.
It's the epi that's a regular epi. But then when you go to the category of locales and you dualize everything, it becomes a regular mono. So embeddings in topological spaces are regular monos. So this is.
You don't need to say that every epi is regular.
No, not every epi is regular. Yeah, but in frames, the epis we really care about, I guess, are the regular epis. They're the ones that form this factorization system. Okay, good. Yeah, so it's just the obvious thing you do in the one case. So for the pre-image, you take the image under the frame map because it gets to be dualized, and then you generate. And for the image, you take the pre-image under the frame map, but it's kind of the only thing you can do. Okay, good. So that was what we were talking about, sublocales. So now I want to start and talk about some topological properties, in particular Hausdorffness. But before I do that, I'm going to want to talk about the product of locales. So the product of locales will be the co-product of frames, right? So how do we compute co-product? And we compute co-product exactly like you compute the co-product for any algebraic structure, right? It's not different for frames, really. So whenever you have any algebraic structure, you can come up with a presentation for the co-product. And what you can do is you can just say, we're going to have one generator for everything in the first thing that we're taking the co-product of, and then the second thing, we're going to have another generator for those, and we're just going to generate the free thing, but we'll quotient it so that the generators in the first part form an algebra that the ones in the first part do, and the generators in the second part form an algebra like for that second part, which is exactly the same as saying that these kind of maps, these things which will become the co-product inclusions, they end up becoming like algebra maps. So that's always how you can define a co-product. So we can do that in this way. But now it turns out it's useful to say, what if we take the co-product injection of something from L and the co-product injection of something from M, and we take the meat of them? And it turns out this corresponds to some kind of basic open rectangle in the product topology. So if we think of this as the product of the topological spaces, if you didn't take this meat, it would just be something which is like, so this is like X and that's Y. And then we say have something from X that might be an open, we're going to get this kind of, this region here, from just saying, if this is U, then this would be, say, I1 of U. And then we could have some V here. And then we get some I2 of V. And then you intersect them, you get this kind of basic rectangle. So these are going to kind of act as the basic rectangles. And so we've taken meets of these two things. And then to get an arbitrary element, you can take joins of these, right? So everything will be a join of these, which makes sense if you think of what is the product topology. If you take the product of two topological spaces, you're also going to have these basic open rectangles forming a base. So everything will be a union of those. So again, it's kind of what we expect. I say more generally, if you have L and M given by presentations, you can come up with a presentation for the co-product very easily. You just take the generators and put them together, and then you just have all the relations that you had. So again, it's quite easy to work out co-products in terms of presentations. Okay. Any questions? Okay. So now we can talk about Hausdorffness. So a locale is going to be Hausdorff if the diagonal is closed. So this is a known characterization of Hausdorffness for spaces, that a topological space is Hausdorff if the diagonal is a closed set. So what do I mean by the diagonal? I guess we can ask. So we have X cross X. I guess we can use the universal property. So
Sorry, Graham,
yeah.
Why am I sure it's a characterization of T1?
So T1 would be points are open.
Yes.
But diagonal being closed is T2. So I can show you now. So anyway, this is how you define the diagonal map using the universal property, using identity and identity. So it's really just what you expect. But why is the diagonal Hausdorff? Well, this is our space and this is the diagonal. Suppose we take two distinct points. then in the product, they aren't going to lie on the diagonal, right? So if we have x1 and x2 in X, then this corresponds to a point lying off the diagonal in the product, but the diagonal is closed. So there exists some basic open set which contains this point and doesn't intersect the diagonal. And this basic open set will be some basic open rectangle, something times something. So this will be some like x1 comma x2 will lie in some u times v. And u will be something which contains x1, and v will be something which contains x2. And because they don't intersect, this doesn't intersect the diagonal, the product, it means that u and v are disjoint. So you're going to have disjoint open sets containing each point. So this space is Hausdorff.
Yeah, no, that's convincing.
Okay. So yeah, so this is the so this is the this is the characterization of Hausdorff, and yeah, we just use the same characterization for locales.
Sorry, what? Okay, I don't want to waste your time too much.
No.
I mean, you say so u times v. This is the diagonal.
Yeah.
And you say that means.
Yeah, because if there were any point in u and v, then then like say there was a point p in u and p in v, then p comma p would be in u cross v, but p comma p lies on the diagonal. Okay. Okay, cool. Good. So we say that this diagonal is closed. So here I've told you how to define the diagonal as a map, but it's not very hard to see that this diagonal is going to be, in fact, a sublocale. So this will be a sublocale. There will be a sublocale corresponding to the diagonal, maybe as you'd expect. So we're saying this must be a closed sublocale. And just if we think about this verifiable interpretation, what this is saying is that the equality relation is refutable. So in other words, the inequality relation is a verifiable property. So a space is Hausdorff if whenever you have two points in the space that are different, you can tell that they're different. So you can think how this would be true for the real numbers. So you can't necessarily tell that they're the same, but you can tell when they're different. So that's what Hausdorffness means. So if we work out explicitly what this map is, so in this diagonal map, in frames, it's going to correspond to a codiagonal map. And what that map does is you can check quite easily that it maps these open rectangles to the meet. So the open rectangle given by u and v goes to u meet v. This is just because we defined this open rectangle u and v by taking meet. That's why we're going to have meet in both places. So that's what it does on basic opens, and then you can extend this to arbitrary opens. Okay, I say this is clearly surjective. So here's a way that you can see it actually does give a sublocale. It's surjective because we can always just take like to map something that maps onto u is say u plus 1 or u plus u. And to be closed, so remember what it means to be closed. So a closed sublocale is something, we saw that the congruence associated with it is going to be something that says that two things are related if they join with some element A, give the same thing. So for this to be closed, it says that when we have this codiagonal map applied to some element S or some element T, these are going to be equal if and only if S join A equals T join A for some A. That's just what it means to be closed. And you can always take this A to be something very particular, and that is the join of all the open rectangles where u and v are disjoint, so where they don't meet. And this actually corresponds to the anti-diagonal. So this open that we get by taking all the open rectangles or the things that disjoint, that gives us all of these things that lie away from the diagonal. So this is actually the complement of the diagonal. So that's kind of what we expect, right? Because for an open sublocale, this A that we have is going to be the complement of that open sublocale. And you can actually, in order to prove things, it turns out you can rephrase this condition a little bit to give something which is nice to prove. But yeah. So for example, we could prove that the locale of reals is Hausdorff. When I first gave this talk at Tackle, I gave the full proof that R is Hausdorff. It's quite a nice proof, but I think it would take maybe a little bit too much time. Yeah, but you can prove it. You can look at my lecture notes for that course for the proof that the reals are Hausdorff. And it's also not very hard to see that sublocales and products of Hausdorff locales will be Hausdorff. So for a sublocal, the idea is if you have a sublocal of x, call it S, and then S times S will be a sublocal of x times x, and then the diagonal will kind of restrict to the diagonal of the sublocal, and so everything will still be closed. And similarly for products, or if you think in terms of, if you want to think in terms of this verifiable interpretation, you might say, well, if we can tell 2 points are apart in the entire space, we can also tell them apart in a sublocal. And if you can tell for products, you can say if they differ, then they must differ in some component, and then you can just tell them apart in that component. So I think there are many ways to see that this should hold. Yeah.
Right. So isn't there a large class of locales for which spatial locales for which Hausdorffness of the locale would be equivalent to Hausdorffness of the space?
Yeah. So I guess I'm kind of sweeping that under the rug at the moment. So if you care about kind of relating this back to the spatial notion of Hausdorffness, a Hausdorff if you have a topological space, and let's say it's sober, so the locale knows everything about it, and you say that this locale is Hausdorff, the locale you get from its Hausdorff, that means the topological space is Hausdorff. But what isn't necessarily true is that if the topological space is Hausdorff, then the locale is Hausdorff. And the reason is that the product doesn't always agree. So even if you have two spatial locales and you take their product, the result doesn't necessarily need to be spatial. When you apply this adjunction and go back to spaces, you get the normal product. But if you don't apply that thing, what you get as a locale might not be spatial.
So if I can come back to my question, do we have a nice class of spaces for which they're equivalent?
Yeah, so any spaces where products of the locales and the spaces will agree. Okay. So for example, locally compact spaces or Polish spaces or things like this, they will agree. But yeah, in general, they don't. But I guess then that's true, that in general they don't. But for this course, we're caring, I guess, about the constructive situation, and you don't want to be doing topology in the constructive situation. So the kind of relationship to the topological case matters less because we would never want to deal with the topological case constructively. But yeah, but if you do care about going back to spaces, this ends up being a slightly stronger condition. It's certainly, if your space is regular or something, that'll always imply that this condition. So, okay. Yeah. So I guess that already gives the locally compact and Polish cases, because then it will be regular. Okay, so I've spoken about Hausdorffness, and that makes us think, what about, we've talked about the diagonal being closed. What if the diagonal is open? So this is related to discreteness. So remember, a discrete locale, I mean, it's just a set. We're viewing the set as a locale. So the frame is just the power set. And we have these basic opens just given by singletons. And you can show that if you take a product of discrete locales, it agrees with the product of the underlying set. So it's still discrete, and it's just the usual product of the sets. I will omit the proof. But now, the diagonal of the product is a subset. So that means it must be an open sublocale, because it being discrete means subsets are open sublocales, right? So the diagonal of a discrete locale is open. So that's kind of dual. So in a discrete space, we can tell when two things are equal. So you can verify equality in a discrete space. In a Hausdorff space, you can verify inequality. And notice, if we ask that the diagonal is also closed, so suppose we have this discrete locale, and we say, now we want it to be Hausdorff, then that's saying that the diagonal is closed. But that means it's open and it's closed, so it has a complement. So in other words, it's open, and its complement is also open. Its complementary sublocale is also open. So both of these are subsets. And this means that it's actually a decidable set. So you can tell whether you're in the set or not. And so we've spoken about decidable equality before. So decidable equality for a set is just saying that it's Hausdorff as a locale. So Hausdorffness for a set gives us decidable equality. Yeah. So again, this is kind of you often see these topological things, like in classically you write, you don't need to worry about all of this stuff because your sets are automatically Hausdorff in some sense. But here you see that these topological notions end up being important even if you only care about sets. But yeah, so it turns out having open diagonal is almost but not quite enough to give you that you are discrete. But we'll see what else you need later. So any questions? Good. Okay, so now we're going to talk about compactness and overtness. So these are kind of more interesting conditions, maybe. So here's the setup. We care about verifiability, right? We want to know. We're saying that topology is the study of these verifiable properties. So suppose I have an open in a product. So we have an open in x times y. And so I can verify when a pair x comma y lies in this open. But what if what we want to do is we want to say, when do I know that, when can I verify for a given y that all of the x's, for all x comma y lies in this open? So this is somehow some kind of like universal quantification over x. So what I'm saying is we have some given open in the product, and we want to know, can I verify for a particular, I give you a y, and you want to know, is it the case that for all x comma y lies in this open? Is that something we can verify? And well, okay, here's one case where the answer is yes. So if x is a finite set, then we can do this because we have like x1, x2, x3, x4, say, and we can check that x1 comma y lies in U because it's verifiable, and then check x2 comma y works, and then x3, and we can do it for x4, okay, and we can do it. And in fact, if you think about it, you can see Kuratowski finite works, like as long as we have some finite indexing set. But if x is an infinite set, this seems like it's not going to be possible, right? Because if x were the natural numbers, then we'd feel like we need to check infinitely many things. So we wouldn't be able to verify that for any natural number, x comma n lies in this open set. Okay, but the point is there are other locales for which this is possible, not just finite sets. So there are other locales that act as finite sets in this sense. And these are precisely the compact locales. So the compact locales are the ones that we can do this universal quantification procedure. And if you saw Peter's talk the other week, then this will make some sense to you. Okay, so let's try and look at this in a bit more detail to see how this is working. So this slide is just going to be kind of for intuition because I don't want to get into all the categorical logic and stuff in order to do it completely formally. But I think the intuition should be fairly clear. So we're considering the set of all y, so all y's, such that for all x comma y lies in U for some open. And we're asking if this is verifiable. So we're asking if this set is open. Okay. So if this set is open, it's like asking whether the complement is closed, right? So we're kind of working classically for a second. So this would be, and if you take the complement, it's going to be a set of all y such that there exists an x such that x comma y is not in U. So we want to know, is that a closed set? But this is the image of the closed set, which is the complement of U. So if you take the complement of U, the set of there exists an x such that x comma y is not in U, this is just the image of the complement of U, and like under this projection map from the product. Does that make sense to everyone? Okay, so saying there exists an X, right? That's just the X that's going to be in the pre-image. So, so this is actually saying that we just want this image of this closed set U complement is going to be this, and we want this image, the image of this closed set to be closed, right? And if we want this to be true for all sets U, this is going to say that all the images of closed sets should be closed. So in other words, we can universally quantify over X if whenever we take the product of X and Y, this projection from X cross Y to Y is going to be closed. So that's going to correspond to this being able to take universal quantification, at least by this somewhat informal argument. Does that make sense? So the set we had, we saw, okay, so we had to take this classical complement, but it turns out it works out. But we said that it's just going to be the image of this complement of U under this projection. It needs to hold for all U, so it needs to be that the image of any closed set is going to be closed. And this is the case we had for Y, but it could have also been true for a whole lot of other spaces. So it must be that whenever you take this product projection, it needs to be closed. And that's precisely what it says to be able to do universal quantification, at least by this informal argument. So that's another thing we want to talk about. We want to talk about when is this projection closed. But actually, we aren't going to talk about that just yet, because it turns out there's a related thing which is easier to deal with. So, but remember this, because we'll get back to it. So before we talk about that in more detail, I want to talk a little bit more about existential quantification. So I was talking about when can we verify universal quantification, but what if instead we want to verify existential quantification? So suppose we have some open in the product, and we want to know, can I verify when there exists some Y, well, can I verify given a Y, whether there exists an X such that X comma Y lies in this open? So is that possible? So if X is just a discrete locale, yes, this is very easy. It is possible. So if this is true, that means there exists some X such that this works, and then you can just verify that that X comma Y lies in U, because U is open, so this is something we can do. So it's very easy if X is a set. But if you go through the whole procedure we did before, but you don't need to take complements, it's asking whether this particular set, we want it to be open, and this is just the image of U under the projection. So it's just saying that this projection must send open sets to open sets. So in other words, the projection must be an open map. So existential quantification over X corresponds to the fact that whenever you take X cross Y, the product projection from X cross Y to Y is going to be an open map. Okay. And when is this true? Well, if this is the case, we say that X is overt. So this is like a dual property to compactness. Compactness, we said it must be a closed map. Here we must say it must be an open map. And you've probably never heard of overtness before, but now I'm telling you it's like this property, which is like compactness, so it's very important, at least as important as compactness, perhaps. So what's going on? So in order to see that, I want to just give another definition. So here's what turns out to be an equivalent definition of overtness. So I'll do it for a frame. So suppose we have some frame. I first want to define this property of being positive. So this is kind of a good way to define not zero. So classically, you just say we can talk about elements of frames that aren't zero, but constructively, we want some better way to talk about this without having this negation. So we say an element of the frame is positive, and we write it A is greater than 0. If whenever we have A is less than some join, the thing we're joining over must be inhabited. So in other words, there must be an element in the set that we're taking the join over. If there were no element in the set we were taking the join over, then we would get 0, right? But this is some positive way to phrase the idea of A not being 0. So whenever A is less than a join, we must have had something in the join. Okay. And we say a locale is overt if it has a base of positive elements. Now, classically, we have that A is positive if and only if it's non-zero. So you can just take all the elements that aren't zero and they'll form a base. So classically, everything's overt. That's why you haven't heard about it. It's not that you haven't heard about it because these things are rare. It's that you haven't heard about it because they are so ubiquitous. Everything you know about is overt classically. And in fact, even constructively, spaces are overt. So it's a kind of, in some sense, you can think of it as a very weak property, but it is very important, and you can use it, like you use it all the time.
Sorry, Graham, what does inhibited mean?
Inhabited means that there's an element of the set. So there exists an X element of S. That's what it means.
It's the same as non-empty? Oh, no,
No,
you can't phrase it like that.
Yeah. So it's a good way of phrasing non-empty. So non-empty would be doesn't equal the empty set. But inhabited is like the constructively good way of saying non-empty. So there exists an element X in the set. Such that true.
But if S was empty, it would be, John would be 0, right?
Yeah, exactly. So it's like the contrapositive of, like, so imagine how you would, like, so if we had that it were possible for X to be less than or equal to the join of an empty set, then, or A would be less than or equal to the join of an empty set, then A would be 0. Now take the contrapositive. And that's essentially what this is saying. But it's phrased all without negatives.
If we're using classical logic, and everything is over, that's what you're saying, right?
Yeah. So if you're using classical logic, being a positive element just means being non-zero.
I see, okay.
And then you can always just take all the non-zero things and they clearly form a base, because you can take the join of none of them and you get 0, and then everything else is already included. But this is a non-trivial property constructively. So maybe it's a little bit hard to think about, but one way to think about it is you can do this existential quantification. So discrete locales are overt because the singletons are positive and they form a base. So, I mean, it makes sense. We said we could existentially quantify over discrete things. The locale of reals is overt. Now, this is not a proof, but maybe it's a kind of intuition. Again, you can see my lecture notes for a proof. So these kind of intervals, they form a base, these kind of open intervals, and they end up being positive. And the idea is, well, we're specifying it by generators and relations, and maybe we don't specify, like, there's no way from those generators just intuitively to get an interval by taking the join of nothing, because all of our like axioms involve taking the joins of very many things in order to get larger than an interval. So there are ways to make this precise, but that's kind of the idea. So the reals are also overt. The reals don't have to be spatial constructively. So this is kind of a new example that I haven't told you about before, but they are still always overt. Yeah.
Sorry.
Yeah.
Reals don't have to be spatial.
Yeah.
Okay.
Yeah, I'll talk a bit more about that later.
And how do we define reals, by the way, constructive?
Yeah, so the presentation I gave a few weeks ago, where you have a theory of Dedekind cuts and you construct classifying locale and things. Yeah. So the points of that are real numbers, but we didn't say whether or not that was a space. So I mean, so that's for the underlying topological, the topological space you get from that is the usual space of real numbers. But we didn't prove that it was actually spatial, that it was determined by its points.
Because you're saying you can't do that constructively.
So constructively, you can't necessarily show that. Yeah. It depends. Yeah. And in certain situations, it's true. In certain situations, like for certain models, it would be true. For certain ones, it won't be true. But, so, I mean, I talk about this a bit later, but an example where it's false is in the effective topos. When everything needs to be computable, it's not true. Yeah. Okay. But we're talking a lot about open morphisms, so let's define open morphisms. That sounds like a reasonable thing to do in this situation. So it's what you expect, right? I've spoken about what the image of a sublocale is under a map. So what you do is you take the image of an open sublocale and you want it to be open. That's what you expect. But then you can immediately prove a certain lemma, which says that a map is open if and only if the kind of frame homomorphism it corresponds to has a left adjoint. So the left adjoint I'm calling F lower shriek. And it needs to satisfy this certain condition. Okay. So I'm not going to go through the entire proof today. But just to give you an idea for the proof, the idea is that it's open, so it maps open sublocales to open sublocales. So what it does, so consider an open sublocal given by A. It maps to an open sublocale given by something, and call that thing G of A. And then you prove that G of A is actually the left adjoint to S star. And that it satisfies this condition, and that's maybe the idea.
And that condition is this something called
Frobenius reciprocity. Yeah.
Does it mean it preserves implication?
Yes. Yeah. It's equivalent to it preserving implication. Yeah. So you can say that a frame homomorphism is open if it's actually a complete hating lattice homomorphism. So it having a left adjoint means it preserves arbitrary meets. And then this means that this condition actually means it preserves implication. So it's a morphism of complete hating algebras. But this is the way I want to phrase it, because later we'll see closed maps and there's kind of a duality, but they aren't co-hating arrows in frames. So this is the one we really want to talk about. So also this has like a logical interpretation. When you interpret things on the logic, this condition ends up meaning that you can take meets out of existential quantification. But yeah, okay. And then there's a converse, which you can also look at if you want, but I think we won't go through the details. The point is there is a way to, it's like, has an adjoint plus an additional nice property is what we need for the map to be open. Okay. So we actually then have the following theorem. So it says that a locale, if X is a locale, we have the following equivalent conditions. So the fourth one is that X has a base of positive elements. So we say that's what it means to be overt. And then the first one is that for all Y, this projection is open. So that's what we are originally motivating our definition of overt. So these two things are equal. But then we also have these two other ones. So the one is that the unique map from X to 1 is open. And the other one is that the kind of corresponding frame homomorphism of this unique map has a left adjoint. So 3 being equivalent to 2 says this extra Frobenius reciprocity condition ends up being superfluous in this case when you're considering this map to 1. So that ends up coming for free, it turns out, in this particular case. So that's 2 and 3 being equivalent. Then 2 and 1 being equivalent, it's related to, so 1 implies 2 because we can take Y to be 1. So if Y is just the terminal locale, 1 implies 2. And 2 implies 1 because open maps are pullback stable. So I'm not going to give you the proof in this lecture. Again, you can look at my lecture notes. But what I will do is I'll prove that 3 implies 4. And then we'll see if we have time to do 4 implies 3, probably not. So I'll show you that if this unique map from the initial frame into the frame of opens of our locale happened.
They forget to record.
No, it said that when you started. So hopefully,
sometimes on the connection.
Yeah, if people online miss something or something, just shout out and say, and I can say it again. Okay, so I'm going to call the left adjoint to this particular map. I'm going to call it exists. Just this is suggested.
Graham, we
Yes.
don't see the slides anymore. I think you have to share again.
Ah, okay. Good. So screen. Do I do a window? Is that or Chrome tab?
No, just entire screen.
Okay, entire screen. Can I do... Okay, there. The one.
Yeah.
And then we go to presentation mode. Okay. Okay. Can you see now? Is that fine?
Yes, thank you.
Okay. Okay, good. So we have this adjoint. I'm calling it, there exists this adjoint to this unique map. So consider what it means for exists A to be true, to be the largest element, the largest truth value. So exists. This map is going to map from elements of the frame to truth values, right? That's what it does. So suppose it's true. Suppose exists A is true. Okay. So that means whenever exists A is less than or equal to some P must be true. Okay, that's kind of clear. If exists A is the largest element, whenever it's smaller than a P must be true. But now exists A less than or equal to P by the adjunction, that's true if and only if A is less than or equal to shriek star of P, because it's a left adjoint, right? So this means that whenever A is less than or equal to shriek star of P must be true. Okay, so that's just using the property of being an adjoint. And now I recall the definition for you. So the definition of this unique map, this from the initial frame, is this thing which takes the join of 1 such that B is true. So it takes in a truth value and it takes like the join that much. So suppose that A is positive, then this condition that we have, that if A is less than or equal to this join, that B is true, that must hold. Because remember, the definition of A being positive is whenever it's smaller than a join, that join must be inhabited. So for this join to be inhabited, we must that P is true. So if A is positive, this holds. And what we want to show is that actually this exists T is the truth value of A being positive. That's what we're going to prove. So suppose that we have this implication holding. So we're assuming that exists A is true. So we have that whenever A is less than or equal to shriek star of P, that P is true. And we want to show that it's positive. So suppose A is smaller than some S, some join of S. So what we can do is we can replace every element of S with 1. So then A certainly is smaller than the join of 1 such that S is an S. But this join of 1 such that S is an S is essentially shriek applied to the truth value of S being inhabited, right? Because if S has multiple elements, that's the same as just having one element if they're all the same and we're taking the join. So this is shriek star applied to the truth value of S being inhabited. And so by our assumption, this means that this must be true, right? We have that A is less than or equal to shriek star applied to something, so that thing must be true. So it must be true that S is inhabited. But that's exactly what positivity means. So A is positive. And so we've shown that actually this is what this adjoint does is it measures the degree to which things are positive. Okay, and now by adjointness, we have this inequality. And when you work it out, this is the join of 1 such that A is greater than 0. Okay. So taking the meat of A, both sides, taking the meat with A of both sides is we get A is equal to the join of A such that A is positive. But this might be a little mind-bending, but this is a join of positive elements, right? It's so the set contains A to the degree that it's positive. So if it contains anything, that thing is certainly positive. So this is a join of positive elements. Okay, so we've shown that it is over.
Sorry, Graham. So you say A equals join of A such that A is positive?
Yeah, it's the join of this is a sub-singleton. So
the two A's are they the same?
They're the same. So this isn't ranging over all A such that A is positive. It's the join of A, and this is a set that contains at most one element. Okay. If it contains any element, that element's A. And it only contains an element if A is positive. So if A is 0, it contains no elements, but then you've got it as a join. But if A is positive, it contains one element and you've got it in a join, but we don't want to do those cases, right? So it's a bit ridiculous, like it's a strange thing, but it is expressing A as a join of positive elements in some like trivial way. Okay, so that proves that this is overt. And then, okay, there's a converse, which we won't go into the details of, but of course, we construct the left adjoint using this positivity predicate. So it's exactly how you expect to do it. Okay, are there any questions? So this is, of course, this is a technical proof, but I thought it was worthwhile because it gives us interesting result about overtness. So now you can prove certain lemmas. The open sublocales of overt locales are overt. this is just because the composite of open maps is open. So if you have an open sublocal, that ends up being an open map. I guess we didn't prove that, but you can prove that. It's not hard. And so then you have a composite of the open sublocal with the unique map to 1, and then that composite is also going to be open. So open sublocals of overt things are overt. You can also prove that images of overt sublocals are overt, and binary products of overt locales are overt. So these are not difficult to prove. But if we just also go back to this verifiability interpretation, so I say that you can existentially quantify over a locale, and now we have an open sublocale. Well, to existentially quantify a predicate over the open sublocale, it's the same as, so call the open sublocale U. To existentially quantify over U, it's the same as existentially quantifying over the larger thing, and then meet with U. So there exists an X such that X satisfies the whatever condition, and it lies in U. So because we can existentially quantify over the larger one, and we can then just say, and it lies in U, we can also existentially quantify over the smaller one. And similarly, to existentially quantify over a binary product, you just need to quantify over the first factor and then over the second factor. So there are ways to also understand this from the verifiability point of view.
Graham,
Yeah.
These are properties that similar properties called compact locale.
Indeed, yeah, that's what we're getting to.
Okay.
So yeah, I guess we started a little bit late, so I'll finish soon, but I will try to get to that. So now I can tell you, though, I told you discrete was almost the same as having open diagonal, but not quite. So in fact, discrete is the same as being overt and having open diagonal. So I'll omit the proof. But in this way, you can think of sets as being dual to compact Hausdorff spaces, because a set is overt and has open diagonal, but a compact Hausdorff space is compact and has closed diagonal. And now I say corollary, if every closed sublocal of 1 is overt, excluded middle holes. Why do I say this? Well, a closed sublocal of 1 will still have open diagonal because 1 has open diagonal. But a sublocal of 1 is only going to be a subset. All sublocales are subsets only if excluded middle holes. We've already seen that. So but if it were overt, it would be a set. So in fact, we know that what must happen is it must fail to be overt. So we know that there must be closed sublocales of 1 that aren't overt if we know that excluded middle fails. And if we're taking our neutral point of view, because classically everything's overt, we can't, in a neutral point of view, actually exhibit something which is not overt. But in a particular model, this will be a way that you can often find something which isn't overt. Okay. So compactness was everything was dual, right? We're taking universal quantification rather than existential quantification. So I need to talk about closed maps. So we say that the image of a closed sublocal is closed. And for openness, we have this adjoint property, right? And it turns out, in some ways, things are a little bit simpler because the frame homomorphism always preserves joins. So it always has a right adjoint. So we don't need to ask that it has a right adjoint. It always does. And it turns out that a map is closed if and only if the right adjoint satisfies this kind of dual version of Frobenius reciprocity. The proof would be exactly the same as the proof we kind of omitted before, but it's a similar way of doing it. Okay. So now, just like before, I gave an alternative view of a definition of overtness, I'll give an alternative definition of compactness. And it might be similar to what you expect it to be. So we say a locale is compact, such that whenever we have a join in the frame of opens that gives the top element, so in other words, it's a cover, it's an open cover. Whenever we have this, there's some Kuratowski finite subset of the set that we're taking the join of, such that the join of it is also the largest element. Okay, so that's what everyone would have guessed, I imagine. Modulo Kuratowski finite, but that's the finiteness we've already been talking about. So, okay, but it's useful actually to have a slightly different definition, and that is we talk about directed sets. So, in a poset you will call it directed if for every Kuratowski finite subset in it, there's an upper bound in the set. So one way you can be directed is by having, say, joins, like finite joins. But you don't have to only have finite joins. There are many ways of being directed. You don't need a least upper bound. You just need an upper bound. So it turns out the locale is compact if and only if, whenever you have a directed set, a directed cover, that cover contains 1. Now, why is this equivalent to the previous definition? Well, if it's a directed set, and you know that there's some finite subset that joins to 1, any of these finite subsets will have some element larger than all of them. So that must be 1 in this case, because it's finite now, and it's yeah. So if it's larger than all of them, we can replace all of them just with this largest element. So, and we know that's a cover. On the other hand, if you know this is true for all directed subsets, you consider the set of all Kuratowski finite subsets, and you show that that's directed, and then you all Kuratowski finite subsets have a particular cover, and that'll be able to work. I hope that's somewhat clear. Okay. And now we kind of observe the following. So if we have that this frame map applied to top is less than or equal to A, using the adjunction, it's the same as top less than or equal to the right adjoint of A. And you can see what this means is, but if we apply shriek of top, the frame map shriek upper star preserves the top element. So that's the same as 1. So that's 1 less than or equal to A. And on the other side, we're going to have, if shriek lower star of A is greater than or equal to T, then it's equal to T. So this means that what this lower star, like this shriek lower star does, is it measures the degree to which the thing is the top element. And in fact, you can now see that it's compact if and only if this shriek lower star preserves directed joins. So if we have a directed set and we have shriek lower star being top, what we want to prove for it to preserve directed joins is that if shriek lower star of the join is top, then the join of the shriek lower stars is top. Why do we only need to check it at top? There are 2 ways to think about it. One is that maps into omega are determined by what they do to top. And the other way is to say we're actually trying to show that shriek lower star of the join is less than or equal to the join of the shriek lower stars. And again, to show that, you assume the one's true and you prove the other. So we assume that S is a cover, that's shriek lower star of S is top. And then we need to conclude that there exists an S in S such that S is 1. That's what the second part says. But that's exactly what we say it means to be compact. That's saying that any directed cover must contain the top element. So I'm going quickly, but I hope this is somewhat understandable. We can go through it maybe a bit again next time, because I must hide this. Because, okay, I'll maybe talk about properness later, or I can talk about it now. So we say a map's proper if it's closed and this right adjoint preserves directed joins. Okay. And then it turns out we have the similar result as we had for openness. So we had about this projection being closed, but also it being proper, or this unique map being proper, or the right adjoint preserving directed joins. And we then get these dual results, like he suggests. There are closed sublocales of compact things are compact. Images of compact sublocales are compact. Binary products of compact locales are compact. So there's very much an interesting duality happening here. But I think we'll maybe go through the details of this a little bit more later. I guess I'll also just mention, though, that a set is compact if and only if it's Kuratowski finite. So this really kind of, again, accords with our intuition. So I guess this is another reason why Kuratowski finiteness is a good notion of finiteness, though you might recall we actually use Kuratowski finiteness in the definition of compact. But we don't use Kuratowski finiteness in saying that the projections are closed. So we do actually somehow get this notion of Kuratowski finiteness falling out of the topology. Yeah, but I will go through all this compactness part in more detail next week. But in next week, what I'm also going to be doing is I'm going to be giving an application of all of this. So we're going to try and give an application. So even if you don't care about constructive mathematics, try and have some kind of application that to classical mathematics that would maybe not be as straightforward if you did it classically. But good. So do we have any questions?
I have a question, but maybe first we thank you for. So I'm quite fascinated about this duality between compact and convergent. I wonder if it's possible to have some sort of abstract framework where one can prove properties of one.
Yeah.
But
Yeah.
the same proof can work.
Yeah, exactly. So Christopher Townsend has an axiomatization in some sense of categories of locales. So it doesn't completely capture the category of locales, but for example, it captures categories of locales internal to any topos. And his axioms, they're actually an axiomatization of order enriched categories. And if you reverse the order, it changes compact to overt and vice versa. And so you can prove things in that setting where you can dualize exactly like that. Yeah, sure.
And does Hausdorff swap?
Yeah, and Hausdorff swaps to discrete, like, or to open diagonal. And
You see, this is in spirit very similar to what I do.
Yeah, because you have the self-dual thing, yes.
Where
Yes.
everything is in classical group theory, everything is conormal.
Yeah.
But the proofs are similar.
Yeah. So exactly. So he has this like research program of proving these things in a self-dual way. Cool. Any other questions? Okay.
Well, actually, I have another question, if I can still ask.
Sure.
So this dual of Frobenius property that you have,
Yeah.
This also relates to what I'm interested in because
because I think your properties are like Frobenius at 0 or at 1.
Yeah,
or,
exactly.
Yeah.
Exactly. Yeah. So do you have a situation in what you where both of them for the junction?
So I guess that's the way in which your thing's quite different, because in kind of this setting, you have the left adjoint being like existential quantification and the right adjoint being universal quantification, and your pre-image map is in the middle. But in your setting, you only have two maps.
Yeah, exactly.
So that's like a little bit weird.
But you still have situations where you want both of them, one for one and the other for the other.
Yeah. So if you have a map that's both open and proper, then that will happen. Yeah. Okay, good. Otherwise, I guess we'll stop sharing, and I'll see you all tomorrow. Oh, not tomorrow, next week. Okay. Good. Bye.
Who else is?
Thank you. Thank you.
Bye. Okay. I don't know if you heard Zurab said he'll see you soon.
Yes.
Okay, great. Okay, goodbye.